title of this notes is Limits Involving Infinity. And in these notes, we are going to look at finite limits as x approaches infinity, infinite limits as x approaches a, and we're going to look at a technique called the end behavior model. So first, let's talk about horizontal asymptotes. So a horizontal asymptote is some horizontal line, y equals b, where b is some number. Right, so if we have our graph, maybe there's our function. We have some horizontal line that function's never going to cross. We're just going to call that value b. It's b units above the origin. So we would say that the limit as x approaches infinity, so as the x value continues to increase forever and ever, that function is supposed to equal b. It's never going to actually equal b, but it's going to get really, really close as x gets incredibly large. We could also talk about going to the left, which we call negative infinity. The limit as x approaches negative infinity. That means going left forever and ever and ever. If we had, I'm actually going to change this picture. We're going to draw another piece of our graph. It's going to look like that. And in this case, as x goes towards negative infinity, the graph is still getting close to the line b. So f of x, the limit is still going to be b. So this happens whenever you have a horizontal asymptote. So if you are asked to find a limit and your function has the horizontal asymptote, the limit at infinity and at negative infinity is going to be the value of that horizontal asymptote. So it's important that you remember how to calculate horizontal asymptotes. If you don't remember, take a minute, quick internet search, how to calculate horizontal asymptote. If it's available to you, you can use graphs and tables to help you. So here we used a graph. If it's not available to you, what you want to do is that horizontal asymptote test. All right, so in your textbook, go to page 71 to figure 211. How do you need to set your table in order to determine a limit at infinity? So the question here is, what do you have to, what table settings do you have to use in order to be able to be sure about the limit at infinity? So think about what your table start could be or what your delta table could be, and how you're going to be able to figure out that. So next, we're going to talk about vertical asymptotes. Okay, so if you have a vertical asymptote at x equals 8, so I'm going to abbreviate vertical asymptote, and I'm just going to say some value a. So think about the graph. Right? Here's some value a. So at that value we have a vertical asymptote, and the graph could be going like that. On that side, maybe it's also going up on the other side. That's just an example. If you ever have a vertical asymptote, then you know that the limit as x approaches the asymptote from the right of the function, it could either be positive infinity, if the function's going up like it does in this picture, Or it could be negative infinity if the function is going down. Let me draw a different function here. It's going down. So we say the positive or minus or negative infinity, plus or minus infinity. Same thing, we have to think about the limit as x approaches the asymptote from the left of the function, and if the function is going up, it's going to be positive infinity. If the function is going down, it'll be negative infinity. Okay, so check out on page 73, example 4. And we see there that the limit as x approaches 0 from the right of 1 divided by x squared is infinity. The limit as x approaches 0 from the left of 1 over x squared is also infinity. We could do this without a calculator. Let's think about this. We know there's an asymptote there because when x is 0, 1 divided by 0 squared, 1 over 0, not defined. So there has to be an asymptote there. If x is really close to 0, that means it's a decimal. Okay? 1 divided by a decimal is going to be larger than 1. And the smaller your decimal gets, the bigger that number gets. And it's going to get closer and closer to infinity. Same thing on the other side. If I have negative 0.001, well, when you square a negative, it's going to become positive. 1 divided by a really small positive number is going to be a really big positive, which is why it's going to positive 50. Notice how the left and the right side limits are the same. So we can say that the limit as x approaches 0 of the function 1 over x squared, it's supposed to be a 1, is infinity. The limit at 0 is infinity. So that was the function 1 over x squared. What about the function 1 over x? The limit as x approaches 0, 1 over x. I'm going to tell you that it does not exist. Why not? Think about what we did for 1 over x squared. Pick some really, really small x values. Look at the limit from the right, look at the limit from the left. See if you can figure out why this limit does not exist. The last thing we're going to put in our notes is something called an end behavior model. End behavior model. So if you have a really complicated function, what you can do is you can find a simple function. That has the same end behavior. So remember, end behavior is the graph at infinity. Is it going up to infinity, down to negative infinity? Same thing on the left. Is it going up? Is it going down? So you have this really complicated function. Just change it into a much simpler function that you know has the same end behavior. As long as g, a function g, is an end behavior model, of function f, I should say of f, okay, let me say that again. G is an end behavior model of f if, this is the condition, if when you divide the two functions, f of x divided by g of x, you get 1 as x gets sufficiently large. Let's look at example. Let's look at example 6 of your textbook. So we have this function, f of x equals 3x to the 4th minus 2x to the 3rd plus 3x squared minus 5x plus 6 all over 3x to the 4th. So we're going to choose an end behavior model. And the end behavior model that we're going to choose is 3x to the 4th power. Yes, 3x to the 4th power. And we're choosing this because it's a much simpler function than this complicated thing. And we know that it has the same end behavior. Here's how we can test that g is actually an end behavior model. We're going to divide the function f by the function g. So everything in function f is going to get divided by 3x to the 4th. Sorry, I was reading my notes wrong. F is just the original function. Sorry if that confused you. What I was writing in was the division. I was a step ahead. Okay. So f is a polynomial. F is the one in red. 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6. Okay. Now we're going to go through and we're going to divide this whole thing by 3x to the 4th power. I'm dividing every single term. When we do that division, let's simplify. 3x to the 4th divided by 3x to the 4th is 1. Minus 2x to the 3rd divided by 3x to the 4th. So let's leave that as a fraction, 2 over 3. X to the 3rd, x to the 4th leaves us with x in the denominator. The next term is going to simplify to 1 over x squared. The next term, minus 5 over x cubed. And the last term, 6 divided by 3 is 2. So that's going to simplify to 2 over x to the 4th. Think back to the last problem we were doing. What happens when you divide by a large x? Remember, we're thinking about the limit as x approaches infinity. So as x gets really, really large, when you divide by a really, really, really big number, you get 0. Think about a piece of pizza, okay? If I divide it into fourths, I have big slices. If I divide it into sixths, the slices have to get smaller. Tenths, the slices have to get smaller. If I take one piece of pizza and I divide it into 100 pieces, each piece is going to get smaller. 1,000 pieces, really small pieces. 10,000 pieces of one pizza, really, really small. As x gets close to infinity, each of these pieces is getting really close to 0. So the limit here is just 1. The limit of f divided by g is 1. The only reason we did that was to prove to ourselves that g is the end behavior model, because this is the definition or the criteria for g to be an end behavior model. What that means for us is that the function, the function f of x equals 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6. This function has the exact same end behavior as this much simpler function that we call g, 3x to the 4th power. So if I want to know the limit as x approaches infinity of f, oh my goodness, I do not want to do all those calculations. Good news, I don't have to. Because it's going to follow, at infinity, it's going to act exactly like g. Okay, well, let's look at g. What happens as x gets sufficiently large? If you have a really large number, you raise it to the 4th power, you have an even larger number. Multiplied by 3, you have an even larger number. So these numbers are getting sufficiently large. We are going towards infinity. for the last part of our notes, we're going to put example 7 on the next page. So that's on page 74 of our notes. Go ahead and put example 7 into your notes. I'm not going to do this one for you, but I will be looking that you've done it when I'm checking your homework. Example 7. After you're done example 7, draw your line. Leave space for a summary in your notes, but don't fill it out yet.